Okay, so this is going to be about IR and mass spec, and then we'll do another video on NMR. So this all has to do with spectroscopy and is how we characterize compounds. And characterize compounds means how we decide what its structure is. Okay, so an introduction. So these are spectroscopy techniques, and spectroscopy techniques are used to determine the structure of a compound. Most techniques are non-destructible. Okay, mass spec does destroy the material, but it requires little to no sample, and it's very accurate. So mass spec is really considered one of the best, if not the best, compound characterization technique. Absorption spectroscopy measures the amount of light absorbed by the sample as a function of wavelength. So what happens here with the different types of spectroscopy is that you have waves, and certain wavelengths will interact with a compound. And so if you have a compound of interest and it interacts and then light gets absorbed and then the wavelength changes, then that can tell us information. And so infrared IR is before the red. So we think of Roy G. Biv and the electromagnetic visible wavelength, and that's what we can see. So infrared is before red. Okay, so in the visible, is the certain wavelengths that we can see. So we can see a wavelength of red and orange and green and blue, indigo and violet, and our eyes actually can detect that wavelength. And so infrared is this wavelength of this length with this amount of energy will cause these bonds to vibrate, and so they'll determine which functional groups are present. So you have to know your functional groups, and infrared will tell you which functional groups are present. Mass spec will give you the mass of a molecule. So it fragments a molecule into certain mass fragments. And so mass fragments is like carbon is 12 atomic mass units, hydrogen is 1. So you can deduce what the structure is based on the mass. NMR is very handy. In NMR, we'll talk about proton NMR, probably more so than carbon NMR, but you'll see it can tell you the number of hydrogens in a molecule. It can tell you the environment in which it's connected to. So you can tell if it's connected to a carbon that's connected to a halogen, or a carbon that might be connected to a double bond. So it tells you about the hydrogens, and that helps you with structure. Ultraviolet spectroscopy is really good for biological molecules like DNA and protein. And we'll not really talk about UV here, but we'll talk about it in chapter 16 when we talk about conjugated systems. Okay, so what we're talking about in spectroscopy is a certain wavelength that interacts with a molecule. And the wavelength is the distance between the peaks of a wave. And associated with a certain wavelength is a certain frequency. If you increase your wavelength, okay, then you decrease your frequency. And energy is going to be associated with a shorter wavelength. So if you have a shorter wavelength, then you're going to have more energy. And so the electromagnetic spectrum, it shows you here. What's important for you to note is that NMR is going to use the radio wavelength, and that's where you have more interaction with the nucleus, the nuclear spin. So you can think of these as hydrogen nucleus. The microwave is kind of what warms up your food because it stimulates the molecular rotation of water. Infrared is one we'll talk about here, in molecular vibration. So we're going to learn if you have a carbon-hydrogen bond, nitrogen-hydrogen bond, if you have a carbon double bonded oxygen, if you have a carbon triple bonded carbon, so you can see what those peak values are in IR. Visible, you all see those in colors, and near UV is, and the UV tends to be spectroscopy for DNA and RNA, conjugated. Okay, so we're just going to keep going. I'm just going to let you know the wavelengths, the wave numbers. This is your units, okay? So these are the units you're going to see in IR. So just know it's going to be reciprocal centimeters. And this is showing you the molecular vibrations that you're going to get for IR. That's infrared. And so when you get IR, you're going to get, you can think of this as the bond. The bond is the covalent bond with two electrons, and these are your nuclei. So these are like, this is a carbon-carbon bond, a hydrogen-hydrogen bond, and when you bombard the molecule with the infrared wavelength, it can cause the covalent bonds to be stretched or compressed. And so here you can see the different bonding frequencies. They decrease with increasing atomic mass, and the frequency increases with increasing bond energies. So you need to get familiar with the carbonyl. Is going to be around 1700, and this is your wave number. So around 1700 reciprocal centimeters is where the carbonyl frequency will show up. And then you have triple bonds. Triple bonds are around 2200 reciprocal centimeters. And then you have, so there's your triple bond again. See this carbon-carbon? And you see the difference between, okay, the double bond here. Double bonds are going to show up around 1600. And your single bonds are going to go a lot higher when it's a hydrogen. So like this is going to be around 3000. And you'll see that you'll also have an NH and an OH bond, and they're around 3500 reciprocal centimeters. So these are just the different vibration modes that you see for infrared. The fingerprint region of the spectra, we don't usually, between 600 and 1400, when we're using IR, I usually teach this in lab. So we do not assign functional groups in this area. So I tell my students that they don't have to memorize the fingerprint area, and that's between 600 and 1400 reciprocal centimeters. And when they're reporting their IRs on their lab reports, I do not have them pick peaks in this area. And I usually always make students pick about 3 peaks, okay, sometimes 2, but 3 IR peaks to identify certain functional groups, FG, in a molecule. So let's pay attention to the 1600 to 3500 reciprocal centimeters. So this is more of the theory, and I'm not going to go into the theory as much because you can read about it. It's more of a more physical or analytical chemistry. But what I will tell you from a practical standpoint, if there's more of a dipole, you're going to see a stronger effect. So here you have a dipole. And if you have no dipole of 0, then you're not going to see an IR peak. Okay, so that's kind of the take-home message. This is the spectrometer and how it works. This is very important, especially if you go into analytical chemistry. I will just say you put your sample in, and a lot of people will have to do this in lab. You put your sample in, you bombard it with a certain frequency, and then you get the IR peak. It's important that you understand that this is what an IR peak looks like, so you know that you're reading an IR instead of an NMR or a mass. We use the Fourier transform infrared, and so you can get more information in less scans, and you use a computer to work out the math. And so then when you get an IR, and you will have sapling homework, okay, so online homework to work out some of these IR problems. And I'd like for you to work also your book problems. So if you can work those, then you should be fine. So in this interferogram, I call it an IR spectrum, okay, then you can see these different peaks. Now in this peak area, this is fingerprint region, so we don't even worry about that. Here, all we have is a CH bond peak, and that's around 2900. So, and that's the CH stretch. You'll find that most things here are a stretch. So if you want to find out, like these are scissors and rocking and it's certain vibrational modes, everything that we care about here that can distinguish between the different functional groups is going to be a stretch. Now, a lot of people think when they're first learning, and students, they think IRs can tell you the structure. And no, not very good. Okay, what an IR is very good at is determining which functional groups are present and which are not present. Okay, so it's really nice to run an IR spectra if you're doing, let's say you're converting a ketone to an alcohol. So if you did something like this, then you would see that the carbon-oxygen stretch will show up around 1700 reciprocal centimeters in your starting material. And then in your product, you would see no carbonyl peak, but then you would see an OH peak, and it would be a broad 3500 reciprocal centimeters. And that would be indication that yes, your reaction did work. Okay? But it doesn't tell you anything else about the structure. It just tells you about the functional group. So you have to be able to report values. We don't worry about this one here, the carbon-carbon single bond, because this is in the fingerprint region. Okay, so the fingerprint region we don't worry about. Carbon-carbon double bond, you'll especially see these around if you have an aromatic compound here. So you'll see a carbon-carbon double bond around 1660. And then you'll see a triple bond. The triple bond's nice if you have an alkyne. You'll see that around 2200. Stronger bonds, so here it is, short and strong, okay, are going to show up at higher frequencies. And you're seeing that here. Carbon-carbon bond stretching. Okay, so if you have an isolated carbonyl, you have 1640 to 1680. If it's conjugated, it's usually decreases about, what's the difference there, 25 to 30 reciprocal centimeters. So you decrease if you have conjugation. And so conjugation is sp2, 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 sp2. So they're conjugated together. This is just, so this is sp3, sp3. So this is an isolated carbon-carbon double bond. And then if you have a carbon-carbon double bond next to another carbon-carbon double bond, it's conjugated, and you see that you have a decrease in about 25 reciprocal centimeters. Okay, so the hybridization, an sp3 hybridized carbon has about 25% S character, and it's going to show up around 2800 to 3000. If you have this CH with about 33% S character, it's going to go higher frequency, and this CH bond is going to be 50% S character, and it's going to show up at 3300. Okay, so once again, we're not worried about this with the fingerprint. This is alkanes. So we just have this here, the CH is an sp3 CH carbon. Okay, so what would we report on this? Alkenes. So you see that this, really you wouldn't even worry about this right here. You would say this is fingerprint. And then you would say, okay, we have a C double bond. So there's your alkene. Okay, so you have that at 1642. And then you have also an sp3 carbon hydrogen stretch around 3000. And then here you have the sp2 carbon hydrogen, and that's at 3080. It's right here. So you can report these three important peaks here. Okay, alkynes. Once again, we're not worried about the fingerprint region. We have a carbon-carbon double bond at 2,119 reciprocal centimeters. This right here is our sp3 carbon hydrogen bond. This right here is likely, yeah, there you go. It's the CHSP carbon hydrogen bond, and that's at 3313 reciprocal centimeters. So there's your three peaks here. This is showing you, and this is a terminal. You see that's a terminal alkyne. You come here though, this is an internal. Okay, so if you have an internal alkyne, you're not going to have this peak here. And see, you don't have that there. It's missing. So what's not present can help you out here. You also have no visible carbon triple bond here. Why is that? Okay, the reason why you don't have this is because this, basically, its dipole is 0. And so if you have no dipole, then you do not really get to see an IR stretch. And here this is your sp3 carbon hydrogen stretch. Okay, functional groups are really good. So when you get into like alcohols, so it's really nice if you know your functional groups by this point. Alcohols and amines, you can see the OH and the NH stretching. They both occur around 3300, but they're going to look different. The alcohol is broad, and it has a rounded tip. Okay, a secondary amine is going to be broad with one sharp peak, and that's because it has one NH. Okay, so it's still, and then the primary amine has two NH bonds, so it's still going to be a little broad, but it's going to have two sharp peaks. And then there is no single signal for a tertiary because there's no NH. Okay, so NH, and it's around 3300. So when you look at this alcohol, you can see here, and my students call that the alcohol belly. Okay, so you can see that you have a broad peak around 3300. Okay, so the amine here is an NH, and you see it's broad, but they're not as far-reaching. So the OHs typically come all the way down here. The NHs are not going to be as high, and it looks like you just have one peak there, so I would say that it's a primary. And it's diisopropyl amine only has one hydrogen because there's only one little peak there. Okay, ketones. What do ketones look like? Ketones are carbonyl, and then they have carbons on both sides. So this is acetone. And then aldehyde, you also have the CH, and then a carboxylic acid here, acetic acid, which is your you also have an OH there. The active ingredient vinegar. So the carbonyl 1710, the carbonyl of an aldehyde 1725, and the carbonyl of a ketone 1710. So the thing is, if you just have the carbonyl and you don't have any other significant peaks, you can say, okay, I got a ketone. But if you start seeing significant peaks like the CH, it's going to come right before the carbon hydrogen sp3. You'll see like two little peaks there. And you can say, well, I don't think it's a ketone because I also have this. So we have both. Must be an aldehyde. And then if you come here and you say, oh, I have the alcohol belly, like the big broad 3500, looks like an alcohol, and I have a carbonyl, then I'm going to go with the carboxylic acid. And that's what you're going to look at here. So here's your ketone. We don't worry about the fingerprint here. And then we start looking here. We have a carbonyl. All right, 17, 18. So we know if we have a carbonyl, do we have a ketone? Do we have an aldehyde? Do we have a carboxylic acid, or do we have an ester? An ester is not put on here as either, but could it be those, or it could be an amide? Okay, so those are our carbonyl functional groups. Well, then you come here, you see you have your CH stretch, and you have this peak here. And so this is, you see this one right here? That's kind of like something, well, actually you don't have anything here. It's a ketone. So a lot of times these overtones are hard to see in the lab in real data. So I would just say, oh, I don't have the OH stretch, I don't have the CH stretch of the aldehyde. We'll look at those. You'll see those are significant. It must be a ketone. Okay, the aldehyde. See, this is what I'm talking about here. So this is your major overtone here. Stretches 27 and 28. Okay, and you also have your carbonyl. So that's where you would say, okay, I have an aldehyde rather than a ketone. So when I'm looking at spectra, the first thing I look at, I always take my eyes and I look in this area here, okay? And I want to say, is there a carbonyl present? And then it's basically yes or no. And that'll determine what functional group I go for. Here, is there a carbonyl present? Yes. There's your carbonyl stretch. Plus, there's the OH stretch. Then you say, okay, I have a carboxylic acid. Conjugated carbonyl compounds. So once you know what functional group you have, you can decide if it's conjugated. And that means it's going to decrease by, like I said, about 25 to 40 reciprocal centimeters. So here you have the carbonyl, and this carbonyl of a ketone is no longer 1710 reciprocal centimeters. It's 1685. So that can clue you in that you have a conjugated system. Look at these. All of these are under 1700. So whenever you have a carbonyl that's under 1700, you might want to be thinking about a conjugated carbonyl compound. Resonance in the amide. So amides, here's your resonance structure here, and amides typically absorb at very low frequencies because of the resonance. So sometimes amides are hard to see because this is low frequency. You're getting into the carbon-carbon double bond of your alkenes. Okay, so it's kind of hard to see. So here's an amide, and you see that you have a very low carbonyl stretch. So amides typically have low carbonyl stretches because of the resonance. You have your CH stretch, which you're going to have that pretty much in every compound because you have R groups, right? You have alkyl chains, so you're going to see that. but here you have this NH stretch. So this tells me with 2 peaks that there's 2 NH bonds. My students used to call this the crab claw. I don't know why, but when they would make funny things like that. So the crab claw either tells you there's an amine, or in this case, there's a carbonyl, so it's an amide. Okay, so carbonyl absorptions above 1725 include your esters. Okay, so esters, look at this one. This one's a strained cyclobutanone, and it's actually a ketone, but it's pretty high up there. So esters typically absorb around 1735. Strained cyclic ketones can also absorb at higher frequencies. So the carbon-nitrogen stretching, we don't usually, you're not going to see a lot of these here. You might see the CN. The triple bonds, whenever you see these, you should either think I either have a nitrile or a alkyne. Okay, so here you have the nitrile. Okay. This is a very unique area because nothing else but triple bonds, I call it the triple bond land, will absorb in this area. Okay, I find this really helpful. So if you were to keep something as a reference, I think this is great because you have your fingerprint area and you're like, okay, when I'm assigning peaks, I'm not going to worry so much about that area. And then I'm going to look, this is what I look first. Look in this region first and see, do you have a carbonyl? Okay, and so that'll determine whether you have, so if it's yes, a carbonyl is present, you could have what? An amide, an ester, a ketone, an aldehyde, a carboxylic acid. Okay, so if it's no, you could have an alkane, or we could just say a hydrocarbon, an alkyne. You could have an aromatic. You could have an alcohol. You can have an amine. You could have an ether. So this right here will decide right here whether you have these present or these functional groups present. If you have anything in this area, it's either going to be a nitrile or an alkyne. And then in this area, you have all of your CH, OH, and NH. Okay, so C, O, N, and they go in that order. And so I typically do not memorize the exact frequencies. I use this as a reference though. If I kind of try to look at the previous slide and just try to figure out what my functional group is and assign a structure based on that. But sometimes if I have to decide between the nitty-gritty, okay, so I've got to decide between an ester and a ketone. And then I might have to come here and look at, okay, a reference, and then I have to make that area, that judgment, whether I have an ester or a ketone based on more reference. Okay, so let's look at this problem here. Determine the functional group in the compound whose IR spectra appears here. Okay, so here, the first thing you do, you say, okay, this is my fingerprint area, so I'm not worried about that. And then here I have a carbonyl. You see how you have a carbonyl? And furthermore, it's pretty far up there, isn't it? Okay, it's pretty high up there. So it's not a conjugated carbonyl, and it might even be an ester. This is an overtone. So this is a nice one. Is this something significant here? Is this an aldehyde? So it's either an aldehyde or a ketone. And let's see what we have here. Okay, so it says a strong peak at the 1720 2 additional peaks. Okay, so right there. So it's going to be the aldehyde. So this small peak from the impurity of water. Okay. So it's an aldehyde. And that's all you can tell is what functional group is present. So, okay, strength and limitations. IR alone cannot determine the structure. Some signals may be ambiguous. Okay, the functional group is usually indicated. Now, this is the important thing when you're writing up lab reports. The absence of a signal is proof that a function group is not present if it's absent. Okay, so you can use your sample IR and confirm whether we have a functional group present. So you're looking for functional group present. Now you always, if you're going to publish, you have to have 2 forms of identification, kind of like when you go get a job, 2 forms of identification for a compound, and IR is not considered one of them. So usually you have to have mass spec and NMR for publications. But the functional group, the IR is really great in labs just to know if you did your functional group transformation. Okay, so one of the identification characterization techniques that is considered very good and very validated is mass spectroscopy. And it is different from spectroscopy. It's destructive. You can't reuse your sample. I don't even really know why it's called spectroscopy because it really doesn't interact with the frequency of light. You basically hit your sample with a high beam energy electrons, and it will fragment your molecule into little pieces. And then you get a lot of radical cations. Okay, so you get a lot of radical cations, and it's these radical cations that get detected. So you put them in a vacuum, you bombard it with these high electron beams, and then you get, and the way it's reported is mass over charge, because you get these molecular ions. And so in this one, if you add it up, you get 30. Okay, so a lot of times this is how you report it. You don't need to worry about that. Don't be intimidated any more than reciprocal centimeters. It's just how it's reported. It's a unit. And here, if you count up, if you look up carbon, carbon is 12. There's 2 of them, so that's 24. And then you go 1, 2, 3, 4, 5, 6, plus 6, because hydrogen's 1. That totals up to 30. So when I'm trying to figure out my mass spec data, I just get a calculator and I add and subtract. Okay, this is showing you what a mass spectrometer looks like. So you have this vacuum area here, so it's a more technical equipment, and you put your sample in here, and then it fragments the electron beam, and then a magnet will separate the ions. Okay, so, and then they go through this rotation, and then they can be detected. And this is what a spectrum looks like. So see, it's different than the IR where you have little peaks like this, right? This is the peaks here. And the height here is the abundance that's detected. Not necessarily that is there, but it's detected. So the abundance is detected. You'll see that the x-axis here increases the mass. So this is going to be your highest mass particle detected. And a lot of times that is just the actual mass of the molecule. Okay, so separation of the ions, like you don't need to worry about that so much. Okay, so how do you look at your mass spectrum? You see that this is a little peak here. That means it's not detected much. Okay. So the abundance of detection is not much. But I guarantee you, if you added up your molecule, so what's your carbon? 1, 2, 3, 4, 5, 6, 7 carbons. How many hydrogens you got? 3, 6, 9, 12, 12, 13, 14, 15, 16. Okay, like I said, you got to get your calculator out when you're doing mass spec. So you got 7 carbons times 12 plus 16. That's 100. Okay, so there's your 100. And a lot of times you might see that, you might not see that, but that is that's significant because that lets you know that that's your molecule. Now, what's detected the most? A mass fragment particle of 43. Well, what's your most stable anion? Okay, so if you broke this particle here, what would that be? So 3 carbons, 3, 4, 5, 6, 7, 8, 9, H9. So 3 times 12 plus 9, 45. So this is subtract 2 hydrogens. So that is similar. That's going to be your tertiary radical. The 85, what's 100 minus 85? 15. Okay, 15 is, what's CH3? That's 12 plus 3. So that's a methyl. So if you take your fragment and you lose a methyl, you have 85. What's 100 minus 57? That's 43. Okay, so you're losing basically 3 carbons and 7 hydrogens. So 3 carbons and 7 hydrogens. So it's something like this. Probably a radical cation there. That's 3 carbons plus 7 hydrogens. There you go. There's your 43. We will not go into that kind of depth. A lot of times you just want to check to make sure your molecular formula equals that end peak. Gas chromatography, this is a common method that analytical chemists use for gas compounds, and it helps characterize compounds, and it basically takes your sample and makes it a gas and then fragments. Mass spectrometry is really good for larger masses, so like of the antibodies and protein polymers. We really didn't know about isotopes until we had mass spectroscopy. So now that we can do isotopes and see that how much we can detect like carbon-13 and carbon-14, it's really been good for carbon dating. So molecules with heteroatoms. This is important for a learning standpoint. Since the carbon-13 isotope is only present in 1.1% abundance, you'll see a little mass plus 1 peak, but not much. So that's where you see the fragment. Now bromine has 2 isotopes, and they're both 50%. So you're going to see bromine, if a compound has bromine, you're going to see a mass peak there. And what's the difference between 79 and 81? 2. So you're going to see an M plus 2 fragment, and it will be equal in height. And that should ding, ding, ding that bromine is in your molecule. So that's where the isotopic abundance is really helpful. Chlorine, you're going to see see the 37. So there's, what's the difference between 37 and 35? 2 mass units. Okay, and what's the difference in the height? So you're going to see the 35, you're going to see it 3 times the height as this one here. So when you see a N plus 2 fragment of a third less height, you can think of that as, oh, that's a chlorine there. Like I said, with bromine, with 50% abundance, you're going to see a mass plus 2, and that's going to signify bromine. Iodide, you will actually see a peak at 127 because iodide will fragment. Why? You all know this. Iodide is very stable. So iodide is a great leaving group. And that's what they're going to show you here is here's your N+2 and it signifies that a bromine is present. Chlorine, you see the little height here, and that's an N+2, and it's a third as large as the chlorine. So sometimes you're going to get some multiple choice questions, and you'll have to decide whether chlorine's present or bromine based on the mass spec. Sulfur has an N+2 that's larger than usual. I think that that's kind of hard to see. Okay, I mean, look at this. It's just hard to see when it's that little. This is just showing you the fragment pattern here. So you have hexane at 86. So this is your molecule. So if you add up your whole molecular weight, you'll see that as 86. If you fragment here, then you get a 71. If you fragment here, okay, and so this molecule here shows up, its mass minus 29. So what does that mean? That means 86 minus these two, 29. So if you lose two CH3 fragments, you have 86 minus 29. Now you have 57. And so this would be, if you split it right there, mass minus 43. And they're just showing you the most abundance is going to be where the molecule is most likely splitting, and the splitting typically ends up following your carbocation and free radical stability patterns. Here we have this here, and you can see, so if you add up all the molecular formula, you would get 86, and then here this mass minus 43, I guarantee you is this, because this would be your most stable, so you would do it like that, like, oh, it breaks right here. That would be your actual most stable carbocation or free radical. So you can see here, and you might like mass spectroscopy. Some people go and study mass spectroscopy and have a whole career in mass spectroscopy. I'm not going to worry about all the resonance. Alkenes, you do have resonance stabilization, so therefore you're going to have a more abundant peak there. Benzylic cation, we've talked about benzylic compounds being more stable, so you're going to see that. Now, if you have water in a molecule, alcohols are very hard to detect by mass spectroscopy because you're heating these up to gas phase, okay? It's so easy to lose a molecule of water, so a lot of times you'll get an alkene, and I've seen this so often in my mass spectroscopy. So you end up getting your major peak is your mass minus 18. So it's like if you have an alcohol, then whatever your molecular formula, you're going to have to subtract 18, and that's probably what you're going to see. And that's what they're going to show here. So if you add up this mass, there's no mass there. That would be the mass that you would see. But if you subtract 18 for water, you're going to see a high peak there, and that's going to be your mass peak, minus 18 because of the water. Here, the 55 would be this right here, and that would be mass minus 18 minus 15. Okay, well that covers all of our slides for IR and mass spec. So the goal for this was just to have an introduction of mass spec and IR, and then I want you to be able to just start practicing problems on getting familiar with the spectroscopy and maybe being able to take some compounds and A, B, C, or D and match structures with the spectra.